Hey everyone, welcome to this presentation for 990B, a project course. So the topic is enhanced IoT-based optimization for hybrid power system in Cartwright Labrador. And then the project members, myself, together with Raymond, Lena, and project supervisor is Professor Tariq Iqbal, as well as project coordinator, it's Professor Amin Etzminan. Okay, going forward, we're going to talk about a couple of things in this summary of content and straight in this presentation. So, amongst which are previous work that we did last semester, current project objectives, contribution from each team members, methodology of the project, result analysis, key findings, future work summary, and the references. All right, so for the introduction, we all know that the energy sector is looking at transitioning from the use of fossil fuels into renewable energy, which will support net zero come 2050. And then by that, we saw a gap here in Newfoundland and Labrador, where some communities which are off-grid are using full-blown diesel generators. That's definitely it's a problem for net zero based on its emission. So due to that, we're looking at designing and simulating hybrid energy systems, which is incorporating both wind, solar, and an existing generating system as a backup in the entire design. So by that, we're able to achieve that for last semester. So this semester, we are looking at creating a SCADA system, which is going to help to monitor the system as well as optimize its performance. So going forward, you can see what we did for last semester. So this is the design of the system that was done last semester. As we can see, we used one of the generators because the existing system there already have about 4 generators. So but we incorporated the lowest generator, which is about 500 kVA, into our system, which is going to serve as a backup system just in case we have low supply from our other sources of energy, which in this design you can see the solar as well as the wind. Okay, so the proposed energy mix, which was the design, it was about 30% solar PV as well as 70% energy, wind energy. So we can see the 500 kVA diesel generator, we have about 16,395 kilowatt hour battery storage, as well as 3,380 kilowatt hour of solar power. Now that's for previous work. As you can see, also this is the result, and looking at the results, you can see the system was really optimized up to the point where you can see that only in January, December, and November, which are the peak of winter, where the times where the backup generator had to come up due to the excess demand of energy, and as well the system was fully optimized with the use of the renewable energy. So we can see from our left here, looking at the cost analysis, we have our MPC as 30 million. Our LCE is 0.352 kilowatt hour, which is really good. Yes, the annual operating costs, it's massive, but for a project like this, that's going to save the use of millions liters of diesel, and also save us the emissions from carbon dioxide. So obviously it's really a good project. And then going forward, you can see our peak energy demand, which was achieved, is 902.24 kilowatts, and that was achieved. So this semester we actually looked at optimizing this system by adding a SCADA system into the entire system, which will help remote system monitoring as well as real-time control and optimization. So the current project objectives, which I've already spoken about, it's to implement IoT-based SCADA for remote real-time monitoring and control and optimization, as well as to optimize the hybrid energy performance to reduce diesel dependency, which I've talked about as well, to enable real-time data acquisition, amongst others, to promote renewable energy integration and into remote communities as well. So the work, this is just looking at the work description, which each of my team members took time to go through to make sure that this project comes into limelight and was successful. Now for the methodology. So this project was really carried out in our renewable lab here at Memorial University. So this system that was heavily involved, the hardware integration, as you can see, is majorly the Festo solar wind energy training system. So you can see most of the equipment that make up this particular system, which we used to simulate this project, which is a solar panel array, wind turbines, rechargeable LED battery, the converter, as well as some measurable interfaces for voltage, current, and power characteristics. So this here is just showing us the capacity for each of the equipment that we used in this particular design and this particular simulation, as well as our training system, Festo Solar.
Okay, my name is Raymond Ore, and I'm responsible for the part of the project that has to do with interfacing the renewable energy system in the laboratory with our SCADA microcontroller, also known as the remote terminal unit. For this project, we used the Arduino R4 WiFi because it has seamless connectivity features which enables it to transmit data in real time. We can go through the specification tables to see the features of the microcontroller and its capabilities. Thank you. So in this section, we talk about the sensors. The sensors are used as field instrumentation devices, also known as FIDs. And what these do is that they collect data on the site, and they are also a medium for implementing control mechanisms. For this project, we're using ASC 712 Hall effect current sensor, and these current sensors are 4 in number, and each of the sensors are connected to the analog pin A1, A2, A3, and A4 on the remote terminal units. Apart from the current sensors used, another sensor we use in this project is the MH electronics voltage sensor. The MH electronic voltage sensor is very great for measuring voltage within the range of 0 to 25 volts. So it is actually used in the laboratory to measure our battery and our DC bus bar voltages. And for us to measure the voltages, we had to implement the voltage divider, which is an onboard feature of the sensor to record the voltages to the voltage levels that are readable by the analog to digital converter on the RTU, which is the microcontroller unit. Right? The Arduino R4 WiFi has great compatibility with the Arduino Cloud because it is actually all made by Arduino. The web application is used by the board to create the IoT Cloud. The first thing we have to do is we have to create an account on the Arduino platform. Then we created the thing and we created the network connection parameters, which is the SSID, and we use the personal hotwire export with WebPA2 security encryption using this AES encryption for security. And for control, we implemented the buzzer. The buzzer is going to allow us to alert for low voltage scenarios. It would trigger an alarm which would inform the operator to activate alternative sources to offset the loss of power in the system. Thank you. On this slide, we have the methodology showing us the comprehensive block diagram of the SCADA system. On this system, you can see that the Arduino R4 WiFi Uno sits at the center of the system. It is the remote terminal unit that collects data from the FIDs, which are the sensors all around the device, and it sends this data wirelessly to the Arduino Cloud, and the Arduino Cloud can be accessed by the main terminal unit, also known as computer, or yes, which also has the human machine interface, which is the Arduino Cloud dashboard. Next slide, we have the offline implementation, which is the Arduino IDE. It's used for writing the sketch, which is the code written in C++, which this code we are able to achieve the sensor calibration. Also, we configured the Wi-Fi module for the communication by setting up the secret key and the SSID details for Wi-Fi communication and internet connectivity. Also, we are able to use the serial monitor to see the real-time readings being collected by all the sensors. Also, we are able to implement with our if-else statement the control mechanisms for the control of the system to signal further actions. We also had a reference multimeter for current and voltage in our laboratory tests. We were able to accurately measure the current and the voltage, and we referenced our measured values from the sensors with these multimeters, and we found the readings to be accurate. And also we simulated different kind of operating conditions by varying the wind turbine speed, and also we kept the solar panel output varied for the time of the experiment. Also, we did data collection. The data collected during the experiment was logged directly to the Arduino Cloud. Based on the plan we set up, we were able to have recordings for many hours of running, but for this purpose of testing and measurement, we took an hour time span, and the sensor readings were fairly accurate, and we used the dashboard to visualize our system and also to monitor the readings in real time. This next slide shows the full setup. It's showing the firstware equipment, it's showing the inverter and the load, it's showing the DC load. The inverter is serving as the AC load on the system, and the DC load is served by an LED bulb. We can see that we ran this experiment. This data logging session was time-stamped. It was an hour time-stamped data logging session when the FIDs were connected to the Arduino, and they were relating through the human interface in real time. And we had the connectivity achieved by using this wireless large area network, which provided our communication, and we're able to have seamless internet access and to access our Arduino Cloud platform. The next slide is the testing and measurement, and it will be taken by my team member, Lena Otabil. Thank you very much.
Hi, my name is Lena Otabil, and I will be taking you through the testing session that we undertook with this design and prototype at the Renewable Energy Lab of the Memorial University. We tested this system for an hour. That is 6 of 10 minute sessions. We had different digital multimeters that were serving as references just to find out how accurate the measurements were. We had real-time viewing on the cloud console, not only the real-time, but we did log the data. And we're going to show that in a graph afterwards. So on your screen right now, like in Fig 11, shows the dashboard display at the start of the experiment. At the beginning of the experiment, we had all the system shut off, all the parameters were down. We can see that it's not exactly zero because of the inherent zero errors in the sensors. So we calibrated as much as possible. And Fig 12 shows the dashboard display for the second 10 minutes where the voltage was turned on. The wind turbine current was at its motor control speed of 20%. So we can see it's just 0.1 amps. The DC load was turned on as well, and that is going to remain constant for 40 minutes of this 1 hour. The AC load is turned on as just only the inverter, not the incandescent bulb at this point. So we're seeing a current of 0.465. Now the solar is also going to behave like the DC load is going to be on for 40 minutes of this 1 hour. So what we're seeing right now is the full load current, that is 0.59. Fig 13 shows that the voltage is still in full value. We had the wind turbine, that is the second one, the second gauge in the Fig 13, increasing to 1.192. That is because we increased the speed to a 40% of the motor speed, and the DC load still remains at 0.4. The AC load still is out, just the inverter is on. And we have the solar current still reading at 0.6. Fig 14 shows the for 10 minutes. The voltage is the same. Now we increased the wind turbine current to a 60%. We can see that there has been a rise from 1.19 to 3.547 amps. The DC load is still around 0.4. The AC load is now in full force. That is the incandescent bulb that is turned on, connected to the inverter. And then we have the solar current still having the full load of about 0.6 as in the prior 10 minutes. Now the fifth 10 minutes shows the voltage is still active, it's still on, the system is running, and then the AC load is still around about 4 amps. Now we turned off the wind turbine. We didn't exceed the 60%, so that is also showing that it's reduced its load current, we can tell. And then the last one, the last fig, that is fig 16, is the display for the final 10 minutes of the experiment. We're showing that the whole system is off, but the voltage is reading 1.3. This is because we have inherent capacitance in the circuit. This takes time to dissipate, and that is what we're seeing and experiencing there. We can say that as a whole, the events that we initiated or triggered were brought up, results that were brought up were predictable and expected. And these are the graphs. The fig 17 is the graph showing the voltages over the test period. So we did the test from 10:50 a.m. That shows where the voltage was in 0, and then it went up for 40 minutes and then came down at exactly 11:40 to the last 10 minutes where it was 0. The fig 18 shows the graph where the wind turbine was running at 0 from 10:50 to 11 a.m. and a slight rise from 11 to 11:10 is where we were running at 20%. So the 40% sees a step higher, and then an even more steep step higher just before 11:30. That is the 10 minutes before, and then we turned it off for 20 minutes, getting to the end of the experiment. The fig 19 shows the DC load current values over the test period. So we can see when the system was off, we see the 10 minutes from 10:50 to 11 a.m. and there's no DC load current. And then we see it rise up for 40 minutes and then drop again for the last 10 minutes as we already indicated. And the fig 20 shows the graph that depicts the PV panel current. So like I said, we run it on the system shut off for 10 minutes and then 40 minutes increased and then stayed fairly constant till the last 10 minutes where everything else was shut off, just like in the first 10 minutes. This graph of fig 21 shows the AC load current where the first 10 minutes from 10:50 to 11 was of 0 value, and then we turned on the inverter, but we didn't connect the load yet. So we can see about a 0.5 amps being recorded for the next 20 minutes, and then when the load was brought on, we see about an 800% increment in the load values. That is from 0.5 to about 4.5 amps. And in general, the power sources and load types influencing the voltage types and measurements were as expected. We had 0 readings for all parameters when the system was turned off, and then the voltage, the DC panels, the DC load, and the PV panels were producing steady output for 40 minutes before And after the shutdown, the AC load, like is shown in this graph right here, was 0.5 under no load, and then 4.5 with full load, underlying about 800% increment. And we realized that the turbine speed also had an effect on the load current values. Now, the key findings we picked up on this project is that IoT SCADA dramatically improves system performance and reliability, because when we included the buzzer, we are able to detect when the voltage drops below a predetermined value, and this prevents unexpected shutdown. So what it does is it will now beep to alert the operator in the room that the voltages are dropping, especially from the PV panel. So that same signal can be used to bring on an alternate power source, so we don't have to face an interrupted supply. Now, another finding is that the low cost of this project makes it scalable for comparable communities like the neighboring community of Black Tickle. In future, we would like to create an algorithm to auto start and turn off the generator, because that is the same signal that is triggering the alarm audio signal or audio alarm. Now, we will like to use machine learning to carry out load forecasting and optimization based on the data that we collected. We also wish to create timely notifications in the form of email and text messages to alert for not only under voltage but other system faults. And then we want to explore further integration with other renewable sources, just to make sure that we have enhanced sustainability and then the best choices. In conclusion, SCADA effectively monitors and handles remotely energy systems that are in place, and it allows operators to know what exactly gives a pictorial view. Now, what we had, our current control mechanism where buzzer alarm warns of under voltage. So like we said, we hope to configure it for other faults other than only under voltage, and the test measurements were accurate and predictable based on the events that we carried out. And so we can say that this project was a success, and that this breakthrough enables Cartwright to embrace smarter and greener energy infrastructure to have a more sustainable future. We would like to acknowledge just a very few of the references that we used in our project work, and thank you very much.